Okay, before you watch this video, you should A, know what know the definition for electric flux, and B, know what Gauss's law is. So pause the video, have a piece of paper and pencil, write down the definition of electric flux, and write down Gauss's law, and review in your mind what you know about each of them, and then return. Okay, this is what you should have written, and this is what you should know. The definition, this isn't very well written, it's a phi sub E, that's the symbol for electric flux. It's the surface integral of E dot dA. E dot dA means the magnitude of the electric field times some small differential area element times the cosine of the angle between them. That gives you a little piece of the electric flux, and if you want the electric flux over some surface, you have to do a surface integral over that surface. In the simple case, where E is constant and the angle between the E and the A is constant over the surface, you can simply do E times A times the cosine of the angle, and we've seen some examples of that. The units of electric flux end up being E, newtons per coulomb, times area meters squared, Newton meters squared per coulomb. That is the definition of flux and what you should know about electric flux. Gauss's law is the relationship, keyword, relationship between the electric flux calculated over a closed surface, doing an integral, and that will always be equal to the charge inside over epsilon naught. So the relationship of Gauss's law between electric flux over closed surface and the charge inside is the statement of Gauss's law, and its application can go two ways. If we know the charge inside, we can calculate the flux through a closed surface, or if we're able to calculate the flux through a closed surface, we can uniquely know what charge is inside. So in this video, we're going to use Gauss's law to determine the electric field for 3 or 4 situations of high symmetry. And we're going to start with a charged sphere. Okay, we have a sphere with 8 charges on it. I'm showing what the field looks like. And what we want to do is we want to find the electric field at this point due to this charge arrangement. And since this is large, it's not a point charge, we would have to cut this up into a lot of little dq's. Take a little piece that would have a certain charge, and then we would have to integrate all the little charges over the whole surface. So here's a little dq, and here's the distance from the field to the dq. And so what we would need to do is to get E at P, we would have to integrate K, right? KQ over R squared. We would have to K dq over R squared, where for this dq, that would be R. For another dq down here, we would have a different R, and we would have to go over the entire sphere with all these little dq's and do this integral. So you can appreciate that that's very complicated. Instead, we're going to use a trick. We're going to use Gauss's law to solve this. So to use Gauss's law to solve the problem of the field at point P, I'm going to draw an imaginary surface And because this is a sphere, I'm going to draw a sphere which is concentric with the charged sphere. An imaginary sphere called a Gaussian sphere or a Gaussian surface. So let me take my pen and let's do it in a different color so we can see. And I'm going to draw a sphere which has a radius that's equal to the distance from the center of this to the surface of the sphere. So that r is the radius of the imaginary Gaussian sphere. And so by symmetry, you should see that every point on the sphere has the electric field perpendicular to the surface. And so we can now use Gauss's law. Let me pause and write that down. Okay, so see if you can follow this. We're going to use Gauss's law, which says that the electric flux through this imaginary closed surface that I created is going to be the integral of EA cosine theta, and it'll be equal to Q inside over epsilon naught. Now notice, what's important to notice is that since the sphere has the same center as this sphere, that the field strength, whatever it is, we don't know what it is, but whatever it is, the field strength is going to be the same everywhere on the sphere. So E is a constant and can be taken out of the integral. Similarly, any little surface area element of this sphere will be faced in a direction which is normal to the surface, and that's the direction of the field. So I hope you can appreciate that the angle of the field and the direction of the area are always 0 degrees. They're always in the same direction because of the symmetry of the sphere. So it's the cosine of 0, which is 1. So since the E and the cosine of theta are constants, we can rewrite this in this way. And so we have the simple case where the E and the cosine of theta, which is 1, is taken out of the integral. All we're doing is we're integrating every little dA, all these little dAs over the entire sphere, which gives us the surface area of a sphere. So let's rewrite that. So this is what we're left with. We have the E, the 1 went away because it's 1, and the integral of all the dAs over the entire sphere is just the surface area of the sphere. That's 4 pi r squared, and that's equal to Q inside, I forgot the n, Q inside over epsilon naught. And so if I solve this for E by dividing both sides by 4 pi epsilon naught, then I get finally that the E equals Q inside over 4 pi epsilon naught r squared, and the 1 over 4 pi epsilon naught is K. So what I get in the final answer is K equals Q over r squared. That means that the electric field at any point from this sphere is the same as if all the charge were located at the center. From the symmetry you can kind of see that, but to actually do the problem using this integral would be very difficult. Using Gauss's law it becomes very easy, and so we've proven that the field due to a spherical charge arrangement at any point in space outside the sphere, any point we pick, is the same as if all that charge were at the center of the sphere, and we simply use the point charge equation. Okay, application 2. We have a long line of thin charge, uniformly distributed. We're assuming it's long, infinitely long, or long compared to the distance between the point P, where we want to find the field, is P, and we want to find E at point P. And so to do this, by making point charges, we would have to cut this up into little pieces. Each little dq would have a little dE. A dq here would have a dE there. A dq here would have a dE there. And we would have to do that integral that we showed up here. Let me see if I can pull that out. Oops, never mind. So anyway, we would have to use this equation, which is a little bit hard to see up here. We would have to integrate all those dq's. This is quite doable, and you can find it in any textbook, but it's considerably more work than using Gauss's law. So let me set that up, and if you have some idea of it, you can try setting it up yourself before I actually show you. Okay, try and picture this in 3 dimensions. What we have is, I drew in the field, but I didn't want to draw every field line for every charge because it was too much drawing. So you should know, I hope you have a good idea by now, of what the field looks like next to a charged rod. It looks like a uniform field. From this angle, if we rotated the rod 90 degrees so it faced us, it would look like a point charge. So the field is getting weaker, but not 1 over r squared, but 1 over r. We've used that relationship in lab. So to use Gauss's law to find this, I make a surface which is like a Coke can or a beer can. So this is a cylinder. You're only seeing it in 2 dimensions. It looks like a rectangle, but this is actually on the ends. It's round, which you can't see. Oops. Right, it's kind of round on the ends. And it passes right through the center of the can. So notice the field will be coming out perpendicular to the surface of the round part of the can everywhere, coming out of the page here and into the screen there. And so if we look at it down the end, it will look something like this up the top here. But if we look at it from this angle, we can see that the field lines are coming out exactly in the direction of any little dA element, right? So if I draw a dA up here, that's going to be pointing up, and the field is pointing up. And so the direction that the dA is facing and the direction that the field is going are the same direction. So let me write that down. Okay, see if you can follow this. So we're doing the integral over the closed surface, and we're setting it equal to q inside over epsilon naught. And notice that we have the ends and the body of the can. So the first thing to notice is that no flux goes through the ends. So we're disregarding that. We're not actually disregarding it. It's just that the flux through here and the flux through this end is 0. So all we got to do is get the flux through the can. And every place, you have to appreciate the symmetry of this. It's hard to capture it in a diagram. Every place over the surface of the can, the field is coming out normal to the surface, because the wire or the rod that's charged is the center of the can. So you've got to be able to visualize this. And so the angle between the E and the A, or the dA, is always 0 degrees. That's 1 E is constant because any place on the surface of the can, the round can, is the same distance, the radius of the can, from the center to the surface. So we have E times cosine of 0, which is 1, and all we got to do is integrate all this area. We don't have to integrate this because that has a flux of 0. And to think about how much area is in the can, cut the can open and make it, cut the can along one edge, roll it out, and you have a rectangle, which is the length of the can times the circumference of the circle. I hope you can appreciate that. And when you do that, we can now finish this problem. Okay, I've reduced this figure and put it away, and I'm just going to finish the problem up. I hope you're still with me. So we're doing the integral over the surface, the round surface of the can, and the field is constant over that surface, and the cosine of 0 is 1, and so we're integrating all that surface area. We cut the can in half, rolled it out, and we have a square, a rectangle, which is 2 pi r, the circumference of that circle that we unrolled, and the length of the can. So that's a length times a length. That's the area, and it's equal to Q inside over epsilon naught. Well, how much Q is inside the can? So the rod is long, and we characterize the charge on the rod by its charge density. So this rod has a charge of Q per unit length L. So to get the Q inside, we simply take the charge density and we multiply it by L. So if this is 10 nanocoulombs per meter, and this is 1/10 of a meter, we have 1 nanocoulomb inside. So that's the Q inside. So then we substitute. We bring this down here. That's E times A. Charge inside is lambda L over epsilon naught. And then when we divide, we'll notice, first of all, that there's an L, the length of the can. So it doesn't depend on the length of the can. If we take a bigger can, we'll have more charge. So the L, the length of the can, cancels. And when we divide by 2 pi r, we would have 2 pi epsilon naught r. So we multiply by 2 over 2, and we get 2 lambda over 4 pi epsilon naught. We want 4 pi epsilon naught, so we get our k times r. And so this whole thing reduces to 2k lambda, the charge density, divided by r. You can see the result we got is what we expected. The field, as we go away from the can, gets weaker as 1 over r, not 1 over r squared, because it's not a point charge or a spherical charge like we had in the first example. Okay, we're done.